Okay, let's get started. Hey, thank you everyone for joining us today. I know summertime, there are a lot of attractions outside, so thank you for taking time. We have truly distinguished visitors from Intel Corporation here today to talk about something exciting about the technologies they work on. We have Jose Roberto Alvarez and we have David Kehlet. I'll introduce them, I'll read their bios, and then I will hand over to them. As you know, this is happening simultaneously in Zoom and in person. So we have several people joining over Zoom. I hope they can hear it. Lauren, please make sure they can hear what the speakers are saying. Okay, thank you very much. So in terms of the intro, I'll first intro Jose Alvarez. Jose Roberto Alvarez is Senior Director at Intel Programmable Solutions Group in San Jose, California, where he leads the PSG or the Programmable Solutions Group CTO Office, defining and implementing long-term FPGA research strategy and roadmaps. He started his career at Philips Lab, and throughout his career, he has architected, designed, and implemented technology products for a variety of industries, including semiconductors, video broadcast, consumer, cinematic post-production, and computer graphics for companies including Philips, Broadcom, Maxim, Xilinx, and 4 successful startups in Silicon Valley. He was co-chair of the MPEG MP20 Roadmap Group, organizing many worldwide workshops in VR/AR immersive technologies, and was inducted to the MPEG Hall of Fame. Mr. Alvarez earned bachelor's and master's degrees in electrical engineering with distinction from the City University of New York. His work has been granted 54 patents. Really distinguished, illustrious career. Let's welcome Jose Alvarez. Our second speaker will be David Kehlet, who is a researcher at Intel working on pathfinding for programmable logic technologies. David is currently developing chiplet technologies to enable a new model of electronic system development, and is principal investigator of the US government's state-of-the-art heterogeneous integrated packaging chiplet design technology project. It's called SHIP project. It's a really, really famous one. Of course, it's going to enable significant breakthroughs in this domain of chiplet technologies. Earlier at Intel, David was vice president of IP engineering, developing SerDes chiplets, communications protocols, signal processing, and memory interfaces on Intel's programmable logic devices. David's team developed the FPGA industry's first HBM2 enabled device and the first FPGA with 56 Gbps SerDes. David earned BS and MS electrical engineering degrees from Stanford University and holds 19 patents. We're really, really glad and honored to have both of them. With that, I will hand it over to you.
Thank you very much. Can you hear me? Yeah. Thank you very much, Professor Bunya, for the invitation. I will be talking about first, tell you a little bit about Intel, and then tell you a little bit about what our CTO Office in the Programmable Solutions Group does, some of the programs that we're involved in, and then David is going to go deeply into one of our key programs. So let me just start by saying that we at Intel create world-changing technologies that improve the life of every person on the planet. That's what we really want to do at Intel. So first, I want to show you a long history of Intel's journey. And here you can see on the left-hand side, we started in 1968 when Intel was founded. And throughout Intel's history, we developed a number of architectures that are used widely throughout the world. I want to draw your attention at 2011, 2018, when we celebrated 2018 50 years. That's around the time where Altera in 2016 became part of Intel, and Altera is what we call now Programmable Solutions Group, where we develop all of the FPGA technology for Intel. So a long, long career. Today, we are at the very right-hand side where we call Integrated Device Manufacturing 2.0, where we are dedicated to being a full functioning fab to the rest of the world. want to pursue product leadership in a number of areas. Starting on the left-hand side on client computing, that it's as you know, widespread all throughout data centers. And AI is being one of the other areas that we concentrate at the network and edge as well. And we believe in accelerating computing and computing systems for and graphics. Mobileye is one of our divisions that is dedicated to be the leader in autonomous vehicle technology. And finally, on the right-hand side, on foundry services, as I mentioned, to become a foundry provider for manufacturing semiconductors in the industry. And this is a lot of the programs that you're going to see that my team works on are related to exactly that, to make sure that Intel provides advanced technologies for the rest of the industry. We are based on a number of values. And I just wanted to show them here because every employee at Intel is dedicated to really being part of this our set of tenets that we work under. We are dedicated to our customers, and so customer first is one of our biggest values, to provide the right products to the industry. Fearless innovation, where we challenge each other to just go beyond what our comfort zones are and continue to innovate. We are results driven because it's great to do research and it's great to develop advanced technologies, but without those results that we see that benefit our customers and the industry, then it's something that is very important to us. We believe that Intel, by the way, as you will see in a few slides, it's a large company, and we want to be able to be one Intel company, meaning we all work with each other and we all collaborate with each other in the different divisions across the company. We value integrity in everything that we do. Everyone, an employee at Intel, is dedicated to be high values of integrity, and that leads into quality products. Quality is an important part of our value system. And then finally, but not least, obviously, is inclusion. We value an inclusive workforce that embraces everyone, regardless of who they are and what their backgrounds are. And this is something that we strongly believe in. As you can see here, we have 121,000 employees. Most of us are technical, so it's a highly technical company. We are spread all over the globe in 53 different countries, and we have a large portfolio of patents. So Pat Gelsinger is our CEO. He's been our CEO for the last 2+ years, and he's dedicated to bringing back Intel to what it was when we started, and being a technological force for good for the world. As I mentioned, we have a number of countries where we operate, but these are the main design and manufacturing capabilities all across the world. We are now dedicated to starting new design centers. Those are the ones that you see there in the color purple. So Ohio is the state where we are building new fabs, new fabrication sites, as well as in Germany and in other countries. So you see, we are spread out all throughout the world. Our main manufacturing plants are in Oregon, Arizona, and New Mexico. We do have engineering and centers in Costa Rica, as well as Ireland, where our Intel 16 technology is now residing. Israel has been a really strong country for our technical development. And you see that we are also very strongly located in Asia. So we're geographically diverse. Which poses some challenges, as you might imagine, because in teams that we have For instance, in the Programmable Solutions Group, we have a very large team in Penang, in Malaysia, and we are distributed in many time zones. Just to give it a little bit of flavor, what PSG, the Programmable Solutions, is, we're about 4,000, a little bit over 4,000 people. We are, as the rest of Intel, mostly engineers. About half of us are located in Malaysia, in Asia, and so we have a very diverse. And by Asia, I also mean India as well. So we have a very large team in India, a very large team in Penang, in Malaysia, and the rest of us are mostly here in the United States. So as I mentioned earlier, we believe that technology is a force for good. We believe that what we do as engineers, as scientists, makes a big difference. And look at what the microprocessor has done in the last 50 years, from a very small device to the current Xeon processors and FPGAs and other integrated circuits that we manufacture. We have literally changed the world, changed how we live. And so that's something that we take very seriously, and we're very proud of that. So we believe that technology is a force of good. And so we have to be responsible, inclusive, lead to a sustainable set of technologies for our world, and then that are enabled in the ways that we contribute to the progress of humanity. So I know this seems like very big goals, but in essence, this is what we believe as a company. Our strategy, as you can see here, is to accelerate global diversity, being inclusive, and to have a social impact. We believe that companies need to have a social impact. And so we have very strong goals for us for 2030, for the end of the decade. And that will lead to having an inclusive leadership and accountability for us, meaning, we need people of different ethnicities, different countries, different points of view to be leaders at Intel and really help us continue to grow the company in a very diverse way. This 2030 RISE goals are the ones that I mentioned there. And we want to achieve an integration that not just involve Intel, but also Intel suppliers. And so we want our suppliers, our partners, to also have the same values as we have. And so we're very committed to have that leadership goal, not just to us, but everybody that works with us. This is a very busy slide, but I'm just showing you this. It's very hard to read, I'm sure, but this is essentially an overview of the kind of technical career paths that we have. And by the way, I encourage you after the talk to come to me if you're interested in internships. I can definitely get you connected to the right people at Intel. But you see here that we have a diverse technical community. We hire mechanical engineers, not just ECE, but mechanical engineers. We have mathematicians, people that have physics backgrounds. In fact, in our factories, in many cases, we hire PhDs to help us, clean the air, clean the water, be always at the forefront of an advanced factory. So as you can see here, many disciplines that we hire throughout those 120,000 plus employees across Intel. This next set of slides is just to give you a flavor of the kind of development that we provide for FPGA specifically. And so if you are interested in development programs using FPGAs, then there's cloud services that are available to you on a request basis so that you can get access to the latest FPGA technology. So now I'm changing a little bit on the things that we do at the Programmable Solutions Group. So FPGAs are used everywhere in the world. And, I get this question all the time, well, will there be a time where FPGAs are no longer useful? And the answer is no, because FPGAs fulfill a very, very specific function in our industry. So on the one side, you have microprocessors, as I mentioned earlier, which are infinitely programmable. Every microprocessor and its subsystems can be programmed any way you like them, but it comes with a price. And the price is that flexibility leads to much higher power, and the fact that it doesn't always run in real time, depending on what processor you have. On the other end of the scale, there are ASICs, basically application-specific ICs, semiconductors that are geared towards a very specific function. And so those are the two main solutions today. It's just very expensive for any company to develop an ASIC. It costs hundreds of people to develop them and tens of millions of dollars. So in between, if you are a designer of a product, you have a set of problems to solve. You have to make a decision. Well, do I need is a CPU, a processor, good enough for my product, and will it meet its power and speed requirements? Or do I need to develop an ASIC, a full ASIC? And then one is expensive. So if you're a small company or you're starting in an industry where things are changing, then what do you do? And that's exactly what FPGAs solve as a problem. FPGAs are basically in the middle. They provide a much faster real-time way to create circuits, and they're infinitely programmable as well, at a much lower power and much more flexibility. And that means that any industry that is nascent, any industry, whether it's be communications, data centers, AI, for instance, they always start with FPGAs to prove the concept, to initiate that combination of low power and high speed. And so FPGAs are exactly in that good spot to do this. And as you saw my old presentation go through, I'll go back to the original slide, which is that mode that most FPGAs are used today, where they're used as accelerators. So accelerators that are tightly coupled with CPUs. On the left-hand side, you see a typical Intel Xeon processor directly connected to PCI Express on any other IOs, including CXL, our newest standard, and this keeps on changing on me. And the FPGA that has access to memory, it has access to very high speed IO, and then provides inline acceleration or special processing in many areas. So that's a typical configuration of an FPGA. Moving on to what the kind of research that we do for FPGAs, it's really divided in three parts. One part is academics on the left-hand side. You can see that we have a number of academic programs for Intel. We work with many universities across the world. And we are also involved in research programs with the US government, with the National Science Foundation, with SRC Jump, which is another organization. And we also have, as I mentioned earlier, an internship program. And so I encourage you to reach out to us if you're interested in internships. We have access to FPGA technologies through a number of services. HARP is one of them. DevCloud is another one that is available to all designers. And then we also have internal research that you see here in the middle, where our PSG CTO office does a number of projects with Intel Labs. There's a labs that it's about 700 researchers today, and they work on technology, developing new technologies in the 5 to 10 year horizon. So looking really forward to new technologies. We in the PSG CTO office, we look at that much shorter time, 3 to 5 years, in developing new technologies. So we work on number of workloads, both domain-specific accelerators. We evaluate current FPGAs. We change the architecture of a next generation of FPGAs, and we always look for essentially programmability. One of the things that I forgot to tell you about FPGAs is that, of course, they come with a prize in development. FPGAs can be hard to program, and much harder, of course, than the tools that you use for a normal microprocessor with normal CPU. But we are always advancing the state of the art to make FPGAs easier to program and provide you that flexibility. In broader Intel, on the right-hand side, we work with several teams across Intel on the architecture and also the business side, the product planning and marketing. And then in a few slides, I'll tell you in detail how my CTO office works with the rest of the organization, just to give you a flavor of how a research organization works with the rest of a big company. This slide is just an overview of the academic clouds that we have. We have a HARP cloud, which is for long-term research. It's not available to the public in general, but if you're a researcher, you can reach out to us, and we will get you access to the latest Intel Xeon and FPGA technologies, boards, and means for programming that. The dev cloud on the right-hand side is much more open to everyone. And so we have teaching materials for professors to develop new coursework and other things that make all the rest of the Intel technology accessible to anyone that needs it. You can look at it at the URL at the bottom, but as I said, reach out to me and I'll get you connected if you're interested. Now, more specifically, I wanted to talk to you about the programs that the PSG CTO office engages in. And this is something that is very near and dear to us. I'll tell you a little bit about the mission that we have in the CTO office, how we drive technology and innovation, what areas we're concentrating in, and what we think of this scalable platform technology. You'll see, I'll mention another technology that I didn't mention before, which is eASIC technology, which is structural logic. And finally, I'll give you a sense of the research programs that we undertake today. So our mission is to explore what everybody calls disruptive technology. So disruptive technologies is a widely used term that basically means things that change the way that we as an industry look at technology. So something that is disruptive. And we want to accelerate our own ability to have a competitive advantage in values and markets that are high value. High value markets are those that are very profitable to us, not to us, but also to our customers as well. And it's all about, again, a phrase that is used very common, high risk and high reward, meaning that we identify areas that are not easy, because if they were easy, well, everybody would be doing them, but we take risks, and the risks are that we may fail. And this is something that in research is well known. You may fail, meaning you may spend your time, you may spend your resources looking for a solution that may not pan out. But that's high risk, but we also want to make sure that if we do succeed, then there's high reward. High reward could come in many areas, right? I mean, you can learn a lot, as you are doing here in the university, or you could also get into an area that is highly profitable as a development area. So high risk and high reward is very important to us. And we do what is also called pathfinding. Pathfinding is yet another term that is very widely used in the industry, and this is exactly how it sounds. We in the CTO office, we essentially uncover not just the technologies, but also the path to making a product. So because we work for Intel and because we want to make a really big difference, we want to look at that path to leads to a product that is useful for everyone. And so this pathfinding is something that we hold very dear and near to us. And as I mentioned earlier, our horizon, if you will, is 3 to 5 years, meaning if we work in a technology, we need to be able to provide a product to our customers in 3 to 5 years. And that's a typical horizon to develop a whole new product. I'll give you a little bit of sense of that a little bit on. So we drive innovation. As I mentioned, we do this pathfinding exercises all the time, meaning which way to develop, find useful ways for new technologies. And then we develop proof of concepts, meaning, okay, it's something that we can provide to potential users of the new technology. And we do that all the time. It could be boards together with firmware, hardware, and things that our users can get their hands on. And then finally, on the right-hand side, commercialization. We are a commercial company, so therefore we really need to make sure that our efforts are really translated into products. On the lower left-hand corner, you see kind of the interactions that the CTO office have with the rest of Intel, and I'll go in more detail on that in a few slides. And on the lower right-hand side of the picture is the kind of integration that we are doing today. This integration on the package is a lot of what we do in the PSG CTO office. So we strive to find novel ways of integrating chiplets, which are small semiconductor devices, and integrate them with very capable FPGAs to provide answers to new areas in the industry. And the reason that we do this is because it's a much faster and economical way of solving problems at the semiconductor level. So this is essentially what we do. We do a lot of collaboration with research entities. This is to show you what our innovation strategy is, which I mentioned to you before. It's all about finding and exploring new synergies with our either U.S. government research organizations, within Intel ourselves, and have collaboration with others. Here on the right-hand side, it's what I usually call a very virtuous circle that what we in the CTO office engage in, where you see that we have very close collaboration with the academic community. We have collaboration with startups as well, since startups are always looking for searching for new technologies. Then we have government organizations, and then Intel Labs, which I mentioned to you. It's a very large component of research for Intel. We are much more, shall I say, practical than Intel Labs, in the sense that Intel Labs really looks for really breakthrough technologies, and in many cases they may not lead to a product immediately. Intel Labs has been working on quantum computing for quite some time and make very good progress. They're working on many other areas that may not lead to products immediately, but we know that they're extremely important for Intel as well. So our innovation areas are just this few that you see here in the middle of this slide. And we do this by necessity because there's so many things that we in the CTO office can work on, but we have to be very strategic and in the areas that we choose to work on. One of them is heterogeneous integration. Heterogeneous integration is what I was mentioning before, is how do you take advantage of the technologies that Intel has to package semiconductors efficiently and in a better way that it has been done before. That's using multiple chiplets, very small semiconductor devices that are attached essentially at the component level to produce a larger product. It's kind of like how boards are done today, PC boards, except at the semiconductor level. And it's kind of oversimplifying it because it's much more complex than that, but essentially that's what it is. How do you build better products more flexibly with smaller components? And smaller components, by the way, that can come from multiple suppliers, not just Intel, but anybody that makes one of those chiplets in multiple technologies as well. It could be analog technologies that use different geometries, the geometries that are now state of the art. It doesn't matter. You just connect them together and make them into a semiconductor product. So heterogeneous integration is something that we in the PSG CTO office look at very carefully. And that leads to exploration on high-speed optical interfaces. And so this is essentially silicon photonics. How do we bring in very high speed optical I/O into the package, and to be interfaced to not just to an FPGA, but Xeon processor or a GPU or any other devices. And this is driven by the fact that, physics, there are physical limitations in electrical I/Os, meaning as you increase your bandwidth, you also increase your power. And as your bandwidth increases, your power really increases exponentially. So there's a point where you hit a wall that you cannot increase the speed of each connection to the point that you can manage the thermal issues that come with high power. And so optical I/O solves that problem because we can do extremely high I/O in the terabits per second with extremely low power. So this is a very, very important area. Another area, which is what we're working here with Professor Bunia and University of Florida, is on advanced hardware and system security. This is how we build chiplets that are secure, and it's a big area of our own research as well. The other one is domain-specific architectures. These are, generically, essentially what the industry is going for now. For instance, a GPU is a domain-specific architecture if you use it for graphics, for instance. And now today, an AI chip is also a domain-specific architecture as well, as Google has done for quite a number of years. But we know that because FPGAs are infinitely programmable, they can implement domain-specific architectures. And Professor Stitt today we've been working with him on that area. We hope to have research programs in the future, because domain-specific architectures really are exactly what FPGAs should be, because not only they fulfill that very specific problem for different technology areas, but also they have the potential of making the FPGA much easier to program. And so that's really a key advantage of these domain-specific architectures, which we've been exploring for the last number of years. Just to give you an idea, we've done neural processing units that are implemented in the FPGA and proven that, under certain circumstances, in some certain domain areas like industrial applications, they can outperform just normal GPUs at much lower power requirements. And then new areas are interfaces in the 3D domain. As you probably have heard, now semiconductors are now being built in the vertical domain, in the three-dimensional domain, stacking components on top of each other. But then there come issues, okay, but how are these components that are going to intercommunicate with each other? And that's where UCIe, a new type of bus standard, chip-to-chip standard, is very important for us. Millimeter wave technologies for 6G, the next standards of communications and wireless. We are looking at intelligent platforms for RF applications. So this is intelligent radios. So there are a number of areas that we're still exploring. And then finally, at the bottom is what we call the ecosystem, meaning, well, so you have all these chiplets, but how do you make them together to work in an ecosystem where everybody can interoperate with each other? They come in together and they are assembled at an Intel factory. Then they make completely new products that have not been thought before. But how do they intercommunicate with each other? So this is a very quick overview of the kind of projects that we undertake. The other of our important strategies is what we call the scalable platform strategy. And the way to look at this is this infrastructure that at the top of it, there's a series of a silicon portfolio, meaning the type of chips that we provide, not just CPUs, GPUs, accelerators, AI engines, but they're all together held on three pillars. One of them is the FPGA that I mentioned before to you, is when industries are starting brand new and there's a lot of uncertainty. So you need programmability, and at the same time, you need the flexibility and power. On the right-hand side, the standard cell ASICs, which is essentially dedicated semiconductors, and in the middle, EASIC. And EASIC is kind of like in between the two. That's the structured logic that allows us to have a combination of the two, and that combination is also some middle point in power and performance. And that's based on a foundation of software, some foundation of interfaces that you see there. And this is how we want to have a series of components and portfolios that span the whole entire industry. And that's what we call our scalable strategy, where we accelerate the access to our technologies for multiple areas. So just to kind of wrap up, and I'll take some questions after that on our research programs. So we are a relatively small team, and in the PSG CTO office, we're about 50 people, a combination of researchers. We have a number of students that work with us in many programs. But we concentrate on 3 different areas. I'm going to start with the one in the middle, which is all about heterogeneous chiplet integration. And as you see, it's a common theme for us to be able to explore these ways of integrating semiconductor components. We are interested, as I mentioned, in the chiplet ecosystem, in the die-to-die interfaces, D2D, and optical interfaces, which is what I just mentioned before. The blocks in green in the middle are the current programs that we are undertaking today. Many of our programs are funded by DARPA. So with DARPA, we started with DARPA CHIPS. That's for heterogeneous integration. We continued, and that program is still running. Ends the end of this year with a new extensions. DARPA PIPES, which is all about photonics interfaces, photonics in the package. DARPA Sahara, that we're working with Professor Bunya and his team on the EASIC technology to make it much more available to developers here in the United States and to provide security. I'm gonna skip and then go through all of the DARPA programs. DARPA Space Beacon, which is a program that we have for what we call free space optics communications in satellites. So these are satellites that are circumventing the Earth at 17,000 miles per hour and communicating with each other through lasers. And there are a lot of as you might imagine, a lot of key research areas that need to be investigated in that. That's the DARPA Space Beacon, the DARPA LTLT for low temperature logic technology. That's and we're investigating how we use transistors that work at 77 Kelvin. 77 Kelvin happens to be the boiling point of nitrogen, so liquid nitrogen. And that's really important for increasing the performance of transistors. The DARPA ITERA program is all about terahertz radios rather. And I mentioned earlier, that's about exploring millimeter wave technologies and intelligent radios. And then going back, the Navy ship program, which is another program that we are very much involved with Professor Bunyas and his team on providing a number of areas, but most significantly security through the what we call the Ripper IP. And then going back to the bottom, the new program called Kanagawa, which don't ask me what the Kanagawa means, but because it's a very complicated and confusing acronym, but it's basically all about making sure that all the optical technologies that we're building are going to be used by the rest of the industry. And you can imagine, I mean, in a data center, for instance, in data centers, mostly the problems that we have today in technology is not so much processing. We have plenty of processing, capability. But the problems are in data memory, data transfers rather. So whenever you transfer from a memory, that's a huge problem. And so data centers today, most of their energy expenditure is just power utilization. And so you can imagine that having orders of magnitude less power requirements by communicating through optical links will revolutionize data centers and will make them much more available, more spread, more AI, more machine learning, etc. So Kanagawa is a program that is sponsored by our U.S. government, which is doing a great job in helping us bring these technologies that may not have a market today, but they will, and they're fulfilling a great function and allowing us to develop all of the technologies that will be critical for the data centers of the future. So that's in the middle. Lots of programs that we undertake. On the left-hand side, we investigate also with the rest of PSG, the Programmable Solutions Group, computation, new computation access to new computation modes for FPGAs, new architectures, and ease of use. Ease of use is very important. As I mentioned, FPGAs can be hard to program. You have to be an expert. So highly recommend take Professor Stitt's classes if you want to know about FPGAs and how do you really deal with them. But they're still difficult to program. There's no if and buts. And so we always look for easier ways to program those FPGAs at higher level languages. We also look for AI and machine learning techniques. And as I mentioned, DSA, domain-specific architectures, and what they're called overlays in general terms. The yellow colors are areas that we are looking for new programs. We don't have any programs yet, but it's all about investigating new ways of new areas. One's in advanced software workflows for AI and machine learning. The other one was future 3D interfaces. As I mentioned, now semiconductor technology is going in the third dimension, stacking components on top of each other. And we want to be able to investigate what are the interfaces of the future, as well as advanced system components. And that's a number of things. It could be either new exotic materials, not just silicon, but other semiconductor materials. And on the right-hand side, the ecosystem and devices, meaning what are we going to do in the future? NGMM, as you see there, is a new DARPA program that it's in blue because it's not necessarily part of my CTO office, but it's really run by the rest of Intel. But we do have collaborations with this NGMM program. NGMM program stands for Next Generation Microelectronics Manufacturing. It's an interest of DARPA to encourage the rest of the industries to use much more exotic components than silicon, and stacking them all in the third dimension, whether it be processing, memory, etc. So NGMM is going to be a really big program for DARPA. Just to very quickly, as you saw, we were running multiple programs, but I just want to give you a sense of a very successful one. The very first one that we've been running since 2017 called DARPA CHIPS technology. And that has led to our ideal because, as I mentioned, we are a commercial company. So clearly we want to make sure that whatever we research, it becomes a product. And this has been very successful. It's led to a new series of FPGAs, which we called, our direct RF FPGAs, which have, the very, very high data converters integrated into the system. And so it's led to a new way of building all sorts of components, multiple antenna arrays, etc. Very, very successful, this program. Also, just to give you a sense of what we call MCPs, multi-chip packages, and they have potential ingredients. So this is really my conclusion slide, that everything that we do for the PSG CTO office is geared towards exactly what you see here, meaning we have an FPGA, advanced FPGAs, and we integrate them with a number of components. We can have direct RF, we could have high-speed PCI Express, Ethernet interfaces, optical tiles, optical chiplets, number of things. And that's really our goal always, to make sure that we can create products that are good for our customers, much faster to build, and better accessible to the rest of the industry. One last one, DARPA pipes, that's on photonics integration. And the idea here, and I'm not going to go to the details of this, but essentially is to convert current products that are, the size of a pizza box, a large pizza box stack on each other to convert them all into this very tiny semiconductor device that you see there on the right-hand side. And what you see there are optical connections, 5 of them, 2 on one side, 3 on the other one, for a total of 10 terabytes, 10 terabits per second access for this data. So quite the bandwidth that we are now supporting with this new technology, all enabled by a DARPA program, and that will eventually be a new set of products for PSG. And that's my talk. I will entertain questions before I hand it over to David. Any questions? Yeah.
You spoke about delivering products in 3 to 5 years. How do you balance that? Because if you try to set off things to go 3 years and you're pushing it back, people lose that urgency. If you set 5 years, people are going to take it for 5 years.
That's a great question. I'll repeat the question. So how do you balance, right? I mean, that horizon that I mentioned to you, 3 to 5 years, because if you say, hey, this is going to take 5 years, at the end of 5 years, you could say, hey, it's going to take another 5 years. Before you know it, it takes forever, right? So it's a great question. How do you balance that? And what we do is, as you might imagine, in any project that you have to have milestones, right? And so our milestones are very critical, and it gives us a sense of, are we making the progress in the research that we thought we were making? Very important to not to fool yourself into believing that you have just such a great technology that you will succeed. So having milestones that will prove to yourself, am I really making this progress? And that could be either power. Are you meeting power goals? Are you meeting performance, speeds, etc.? And we talk to potential customers as well, right? Because it's also very easy to fool yourself that you're creating the best solution for something that nobody will use. And though that's also fun to do things like that, it doesn't lead to good products. And so it's a good question, and not an easy one to manage. You could definitely get fooled with that. So you have to be very careful. Good question. Any other questions? Anything you can ask me.
Last one, I think. So these are really exciting do you anticipate new applications domain, some space, healthcare, or any domain using these Intel technologies, which should be hopefully production soon for the enabling industries?
Right. So the question is, if I can paraphrase it, what is our expectations for these technologies that we are developing in new areas, like medical and other areas that we have not seen? And it's a good question. And our goal as CTO Office is to make sure that what we are developing can be used in multiple industries. And that's really important, in industries that maybe we have not thought today. So that's why we always go back to the fundamentals. So we always need to choose areas that we know that will have products in perhaps markets that we have not thought about. And that we do by making sure that we have technology that can be commercialized. They commercialize at a good point. Meaning, and what is a good point? It means that we can create a product that it's going to be used by a large number of people. A related question, for instance, is many of these research programs that we undertake, a lot of the times we have 1 or 2 customers that come and say, hey, we would like to use your product. Then we have to really make a decision. Well, this customer may not provide us with enough components that they're going to buy to justify what it takes us to develop that product. And to develop an FPGA takes hundreds of millions of dollars. It's big undertaking. And so that means that we need to have a way of recuperating that investment, clearly. So that means that new FPGA that we create better serve many markets. It better serve market, for instance, of let's say that we are targeting to the AI market. Well, it better serve markets that use AI and machine learning in different areas. For instance, it may be industrial, where you use an FPGA to have a combination of a very simple AI inference engine, but also a vision engine together in one package. Or it could be for medical, where you're creating a new MRI machine, and then you use just simply, image processing for that. Or it could be automotive, where you use for, to manage, braking systems or even infotainment. So that really goes into our decision of how to create a product that can be used in multiple industries. So yeah, very, very careful decision. And we have a whole set of people, by the way, that are called product planners. And the product planners are technology people. They don't do design, but they know markets. They know how to talk to customers. They know how to go out there and figure out, well, in the future, it seems like these customers are going to develop these future products. And so we think we go back and say, okay, engineering team, why don't you develop us a product that does that? And that's really the conversation, if you will, that we have. Mhm. These are in general terahertz radios. Yeah, terahertz. So that's it depends on the market. That's related to the previous question. But it's under 50 watts. Yeah, much lower than that in some applications. And so the related question is this: we had a customer that wanted a multiple array antenna at 1 watt, and the current technology does not allow us to do that. 1 watt, that's amazing, but this is the kind of things that you need to judge, right? It's like, yeah, this is what you need, but technology today cannot provide it. But that means that we need to know, okay, but is there a way to develop those technologies? And that's where Intel Labs comes in. Intel Labs comes with solving really those problems that we know that we're far away from reaching that. But you guys at Labs, you can think about that while we think about intermediate products that are in the 30 to 50 watts per system. Any other questions? Yes. Yeah. What specifically would you like to know? I'm sorry. Can you repeat that? Yeah. So the question is, Intel. I'm going to paraphrase your question. This is a good question. So historically, right, Intel fabs, our fabrication facilities have always been used for Intel products, Xeon and other products. And so now I mentioned that Intel is having this, open approach, this IDM 2.0 approach, and opening to everybody else. Why is that? Well, it's a great question, and it has to do with a multiple number of reasons. One of the reasons, by the way, and this is why the government here in the United States have instituted this new huge program called the Chips for America Act, is to be able to help the United States regain our technological advantage in making semiconductors. Today, less than 15%, 12% of all semiconductors are made here in the United States, and Intel is one fab here that makes, advanced semiconductors. The only one, the last one. Not that there's the only fab here in the United States, but other fabs do not necessarily work on, very advanced technologies. So Intel has realized that, that we need to change. We need to be able to provide that technology to the rest of the world as well. And so that quite honestly requires that Intel thinks differently. Things like other fabs in Asia that provide services that can be used by anyone, not just for our own, but for anyone. And that will not just provide a service to us, to the United States, to continue to be ahead of the technology, but also will provide the what we call the assurance of the supply chain. I think COVID really showed that supply chains around the world are very, very, very tenuous, very brittle. And you heard about cars that couldn't be sold because manufacturers couldn't get access to a $2 chip. And so for a $2 chip, you couldn't sell a $40,000 car. And that's because of this, issues with supply. And so having domestic supply for us would be a much more convenient way to having better solutions. So yeah, so that's the main reason. Okay, I'm going to give it to David. We can ask questions much later. So I'll very happy to introduce David Kehlet.
Great. So first off, thanks for the welcome to Florida with the lightning show for the last 2 nights and the tornado warning this morning. So it's a lot more exciting here than back in California. And I just want to say that Jose provides a fantastic environment for us researchers in the technology office. And it's really a lot of leeway and a lot of trust that we're going to be developing great things for Intel and for the United States. So it's excellent environment that I really enjoy. I wanted to talk today about a couple of research applications, really applied research, technology applications that I've been working on along with a team of others in technology office that I think have some really interesting elements to them that I want to share with you. So as he mentioned, I'm working right now largely on this chiplet design technologies project, and it's a project that Intel won on a contract with the U.S. government to develop heterogeneous integration prototypes and technology. And part of this was that the government asked us to propose projects that would help us develop interface IP, protocol IP, and security that would help the defense industrial base develop and use chiplets. Chiplets are these heterogeneously integrated silicon and other semiconductor devices that will co-package together. And our idea was we're going to develop this technology to enable these folks to really focus on what their application is, and less on the, how do I achieve guided eye communication? How do I provide security? That we would do that, and they can focus on their high performance D-Day converters, their proprietary photonics technology, and less on how to package that up into something that could then be used by the defense industrial base. So we've developed some code for chiplet hardware security, and it's taking experience that we already had with FPGAs that already exists on Xeons, already exists at the FPGA level. I want to apply this to chiplets, these small semiconductor devices. And really our threat models that we want to defend against, we want to defend against counterfeit chips, malicious chips. We want to defend against unauthorized use. That we can tell that our firmware comes from a trusted source. And we want to protect chiplet firmware from IP theft. Now, all these three things here are possible today on many heterogeneously integrated devices. And we want to say, hey, we will develop a framework that allowed to defend against attacks in these areas. Now, what I'm going to talk about is using what we call classical public key symmetric cryptography. So people here who understand cryptography, public encryption, this is not new. So I didn't invent any of this, RSA, Shafi, and so on, but it's a really interesting application of this. And given that we're trying to do these on very small chips, we've got to do this in a very small area. We don't get a big SoC, you don't get to use a whole security device manager, 2x2 millimeter part of your chip to implement all this. Okay, so the first thing is, can I trust the chiplet? So this is, we want to do chiplet authentication. So folks who aren't familiar with public key cryptography it has this amazing property. You can prove to anyone you have a secret without revealing the secret. So this is a fantastic mathematical breakthrough from over 50 years ago. And the way it works is that you use these algorithms to create this public and private key pair. And you hide the private key into your chiplet here, and you store the public key over in the other chip. Now, anybody can ask this green chiplet here to create a signature from a message. And the signature is this encoded word that can only be created if you have the message and the private key. Now, anybody can take that signature and see if you really have the private key. And nobody can figure out what the private key is. So this is really, really cool technology. So because we can use this at any point in the supply chain to check if the chiplet is authentic. So this is really, really helpful. All the way from when the wafer's first fabbed, all the way through assembly, through test, to receiving single die inspection, to multi-chip package integration, even installed in a system at that point you could say, could you verify that all your devices are authentic? Okay, so the way this is going to work is this base dial on the right, it wants to authenticate the chiplet. Finally, this is a Gen 1 chiplet here. So we generate that public and private key pair that I mentioned, and we're going to take that private key and secretly store it in this chiplet here. So the chiplet algorithms can access it. Now we're going to use our SHA-384 and ESA algorithms for hashing and signing and testing. The way it works is chip on the right generates a random number, sends it over to the chiplet and says, please sign this. Chiplet signs the random number using these algorithms, sends the signature back, and the base die tests the signature. So then the chip on the right can tell if it succeeds, yes, it's an authentic chiplet. If it fails, it means the chiplet did not get the right response. It might not be a genuine chiplet. So the first question I have, anybody, why would you use a random number at this point? It's sending this number across. This chip is signing it. So every time you send a different number across, you get a different signature back. But then it can still test that signature. This guy knows what message the random number he sent over. It knows the public key, and you can say, yes, this correctly calculated a proper signature given this random number. And whatever its secret key is, I don't know. I only have the public. Okay, well, I'll tell you. The reason you use it for random number is to prevent a replay attack. So imagine somebody's watching right here. And they see this number go across, and they see the signature coming up. They go, aha. But even though I can't calculate the signature, I've seen this number come across. And I've seen the signature I'm supposed to produce. So next time this comes across, if this weren't a random number, I would just say, aha, I can match this up at a table of messages and signatures, and then send back the signature and fake out the guy on the right that I have the actual genuine secret key. So that's why you want to use a random number. It prevents this kind of replay attack. Usually this is a very large number, 384 bits or so. So it's just innumerable amount of numbers that you can produce here. There's no way you could save up a table big enough. Now, the good thing is the chiplet, it might be the chiplet is the trusted device, and you don't know if the base die on the right is the one. You can just reverse the roles and use the same protocol. And so there are cases where people want to do co-authentication. Each one authenticates the other. And in our environment, generally, it's like it kind of works its way down from the top. And then the system decides it's going to trust the FPGA main die, and the FPGA main die is going to go ask the chiplet, do I trust the chiplet, and then report back the results all the way back up. Okay, so next question. What's the best way to attack this scheme? I think as a Florida have done this, I saw the paper out of Joanna's lab. Okay, well, the best way to do this, go find the private key. You can't break this algorithm, reasonably, at least not today. But go find the private key. And so the difficulty with these things is that it's really hard to hide something in a chip. Very determined people can find anything that you want to hide in the chip. And you can make it more difficult for them. We use a technology called anti-fuse, where instead of blowing a metal fuse, which you can just optically inspect the chip and see it's one metal fuse, you have to actually, you can't even section it and see this. You really have to electrically charge it up and then see the results of sensing these anti-fuses as an electrical state, which is itself, it's possible to do that. So that's a good best way to do this. That's something that it's really hard to hide a secret inside a chip. You have to assume that you can't really do it against the determined adversary. Okay, now this is where you get very practical being an engineer. Suppose that every chiplet has a unique private public key pair. I started out thinking, like, each class of devices, if it's an Intel F tile, you'd have one key for the Intel F tiles. All F tiles would respond the same way. And some folks said, no, you might want to have an individual key for every device. That way you can tell, has that key been reused? Because this guy could find out from that public key, has this thing been reused, and avoid somebody trying to just duplicate the device. And just somehow figure out a way to completely copy this device, you can detect it. So in this scheme here, suppose every one of these chiplets has its own unique private key. You need a unique public key for it. So then all of a sudden this thing on the right side has to maintain a massive database of all the different public keys for every possible chiplet it might encounter. And this is awkward. This is not very practical. So the cool thing is you have the chiplet provide its own authentication public key. It's like, oh, I'm going to trust this device to tell me the right thing so that I can authenticate that it's a genuine device. So how can this possibly work? Well, what you do is we're going to create something we call a certificate. I'll show you this on another page, what the certificate looks like. And that certificate has the public key for this chiplet. And this chiplet has its private, the secret private key, but it's also got the certificate with the public key in it. Now, the certificate has a signature from a certificate authority. So there's some other third party out there that said, yes, this is an authentic public key, and they've signed it. So we say, hey, chiplet, send me your certificate. And we'll go check the certificate. Using the public key of this third party's certificate authority, we say, okay, this is a valid certificate. Therefore, I can trust the public key that's inside it. Now, different chiplets can have different public-private key pairs, and the base type only needs the certificate authority's public key. So this way, this can actually talk to a chiplet it's never seen before. As long as it sends a valid certificate across, you can do the whole authentication. And this is a really powerful means of indirection. So after you do this thing, then you do the authentication protocol on the previous page. Now you have the public key, and you can tell if the device is authentic. So here's a standard certificate format. What it's got inside here is the chiplet's public key. This is what I'm going to use to authenticate the device. Then it has the signature in the certificate of this public key and the certificate authority. So those are the key pieces of it. And this indirection means that you can authenticate in chips. So it's a very powerful algorithm that was developed again about 50 years ago to perform this operation. And we're applying it now at chiplet scale. So this has a real potential. Okay, so the next thing we want to do, we want to make sure that if somebody's downloading firmware to me, can I trust this firmware? Because, that's a real common attack. You load firmware into a target device and get it to do whatever you want it to do. You could have it go extract anything that's inside a chip and tell you this would be a good way to attack this. And a lot of people do this kind of thing, like, figure a way to pull out the firmware out of the chip and modify it, load it back in. Okay, so the way that you tell if your firmware is authentic is you develop this public-private key pair. The public key is stored in the chiplet, so you don't have to keep the secret. It doesn't matter if somebody can find it. The private key is held by the firmware developer. So the firmware is signed by the private key by the firmware developer, and the private key never has to exist in hardware. So this is pretty secure this way. The firmware is loaded on the chiplet, and the firmware signature is tested by the chiplet. So I can say, yes, this firmware comes from a trusted source. It looks good. I can load it and start executing. Okay, and our last one here, we're going to defend the IP in the chiplet firmware. Now, a lot of these advanced devices, almost all of them have microcontrollers inside them. Many of them have many microcontrollers, like controlling different SerDes, controlling different ADCs. They do proprietary calibration techniques that they don't want copied. It's their IP. So you want to keep your firmware secure. So this is probably more of the encryption that we're used to here, which is the symmetric key. So the firmware developer over here has the symmetric key, encrypts this firmware as plain text, and then you send it down to your main die. It could come from the server, it could come over the air, it could be stored on the main die. It's encrypted firmware, so it's pretty secure. Now, the chiplet does have the hidden symmetric keys, the secret symmetric keys. So it's still vulnerable to somebody doing a physical attack. Nevertheless, the scheme here is you send it across, this guy decrypts it, and if it successfully decrypts, then you can execute it. And the reason this is really interesting is now, by creating these multi-chip packages, we created a new attack surface, which is the boundary of the main die and the chiplet. These sort of things exist on die. Often those are harder to access than things in between die, where you can more easily probe them. And so, really, one of the things that I've been encouraging my sponsors in the government to do is, hey, you should require that firmware for these devices should be encrypted at chip boundaries, and then depend on at the target, then it finally decrypts it and then you can execute it. So we happen to use SPY as a security communications channel. We send our control messages back and forth here, the random number, the request for signature, the signature goes back. We picked SPY because it's typically used by ADC DACs and other peripherals. And we just use a simple read-write protocol over SPY for this. And the reason it's interesting is because eventually some supply chain concepts are going to require that chiplets be authenticated, so that you could therefore verify the supply chain all the way from the fab into the. Okay, so the second topic I want to talk about is protocols for chiplet interoperability. And Nibs did most of the heavy lifting on this one here. I don't know if you folks have met Nibs Doraj. He's a senior engineer in our department. He's also helped with us in the last 2 days. And when you created a chip here and a chip here, you've got to move data from one to the other, control data, something. And so you need a protocol for how to do reads and writes, or how to stream data from back and forth. And up until we did this, everybody creates their own thing. This high performance ADC DAC, José talked about, they created their own custom protocol for how to send data and commands back and forth. And they spent effort in an area that wasn't really providing additional value. Their value was this really cool 64 data samples per second ADC DAC. That's their IP, not how do I move data, talk to the other chiplet. So the question is, well, what protocols do you do? One of the great things about FPGAs, and when we worked in our IP engineering group, that in the main engineering body of Intel and Altera before that, many protocols are great because the FPGAs are perfect for that sort of application. More protocols, the better. And so we asked around, we used our own experience, we asked around a lot of folks, and I got this from a professor at the University of Michigan. And he gave me this book. If you provide Axie4 Stream and Axie4, it will cover all use cases for machine learning and digital signal processing. So it was a strong validation. I surveyed a bunch of other people, and it really came down to they needed SPI, that one I talked about, or just a real simple serial communication protocol. But for their high bandwidth communications, Axie4 was big because if folks haven't used this, is a very common and not even modern protocol, but it's very common for module to module communication on die. Same clock domain, same cycle response. That you want to send data, the other side has to be ready that same cycle. And if they're not ready, you have to respond that same cycle correctly. So what we're going to do is we're going to create protocol adapters. And the applications are going to think they're just talking to the Axie4 leader, they're talking to Axie4 follower, and vice versa. Therefore, they don't spend time fooling around creating this handshaking and everything else that goes on here. They just focus on their application. And you might see a lot of memory IP out there uses Axie. A lot of catalog IP from Synopsys Cadence uses Axie. This is a really good common interface. There are more advanced ones, CXL, much more advanced protocol. But in these kind of scenarios, you often don't need distributed shared memory, which CXL is great at. You just need, I want to do region writes to the module that's next to me. Okay, so some various applications, how do we back up what you want to do? A lot of people looked at this and said, we want the protocol that everyone uses for die-to-die communications. It doesn't look like it's never looked like that. It starts at the application. You have to make the protocol suit the application and not the other way around. So in a streaming application, you got this massive parallel. The width varies by application. You need high utilization, high efficiency, and low latency. Data usually arrives every clock. This is real-time data. So really, often this communication is synchronized exactly to the sample frequency. And you don't even need a valid indicator because data is valid every single clock. So this use case matches Axie4 Stream. I've got a couple more use cases here for a memory application. You want to do read and write transactions. Again, you need high utilization, low latency. This matches Axie4. Now, Axie4 is a lot more sophisticated than Axie4 Stream. Axie4 Stream is very simple. Some people claim it's not even a protocol. But Axie4 is a full-on make your writes, your read requests, read responses. Finally, there's a light version of this. If you're just doing control and status update, you don't really need high bandwidth, but you do often need fast control, especially in a real-time system. Okay, now we're going to talk about how do you do this over a die-to-die interface. So here's the challenge. The leader must react to the follower's ready within the same cycle. Now, if the follower's ready over on another chip, you cannot get, first off, you're not synchronous. You could be 0 ppm, meaning it's running off the same reference, but it's not the exact same phase. Controlling the phase between two chips is generally not worth it. And furthermore, it's going to take probably more than one clock cycle to get from the chip on the right all the way back to the chip on the left. You have to assume that. In fact, almost inevitably with a high performance interface running at very high speed, it's going to take several cycles for a signal to get from one chip to the other. So straight Axie4 does not work because the clock phase difference and the cycle delays. We need these adapters to allow for phase and pipeline delays. So what we're going to do, and Midge came up with this, and actually it's a common scheme for protocols, is we're going to do a credit scheme. And the leader cannot send something unless the credit count, it's going to keep a credit count. Unless that credit count is greater than 0, it cannot send a word. Now, this is done by the adapter. This guy just does whatever he's going to do, thinking it's all monolithic. This adapter here is going to manipulate the valid and ready according to the credit scheme. Now, the follower side, sorry, the leader side decrements the credit count every time it sends a valid order. That count's gonna go down. The follower is gonna return a credit when an entry is vacated from the follower side adapter. So when this guy finally pulls the word out, it goes, oh, okay, now I can accept another word. I'll send the credit back this direction here, and this adapter here is able to increment the count. So that's these two steps here. Follower side returns it, the other side increments the credit count. Okay, so here's another way of looking at this thing. You've got your actually for interface, you've got your credit manager here. We do some packetization because actually for has multiple buses and the utilization of all those pins isn't necessarily very high. So we create it in a packet. So actually 4 has 5 channels. We actually have 2 channels, just a TX and an RX. And so we'll packetize it. So this thing will send all the way over here. Here's the credit FIFO, and then here's the actually for follower who's just thinking they're talking to their neighbor module on the same button. So there's the data going over here, and then credit return comes back here. So that's great. Now this is going to work. Suppose the receiving side can only support 1 credit. This guy here is the credit manager, says, okay, there's 1. I send my word, I decrement it 0. I have to wait. It's all the way here. Data comes over here. It's going to see it. And finally, this guy pulls that word. It goes, okay, I can send a credit back here. And this guy can increment. So the good news is the protocol works. You will not lose any data with this scheme here. But the throughput's terrible because this guy's going to stall after it sends its first word, waiting for this round trip delay of the data word going there and the credit return to come back. So we call this a bubble. You're going to get a huge bubble after every TX word gets sent. So this begs a question. And the question is, how big does that FIFO have to be there? Okay, because the leader must not overflow the RX side. So it has to stop sending after the RX FIFO size number words. So you pick this side here, it can send that many words, that has to stop. So you have to create a credit scheme so this will stop once this FIFO is full. Because it doesn't know when this guy might just say, I'm not ready, I'm not ready, I'm not ready. So this whole FIFO could fill up. And this guy better not have sent more than will fit that FIFO, otherwise you're lost data. Okay, so the first thing you know is you need the number of credits to match the size of this RX credit FIFO. Okay, that's good. So now credits equal the size of FIFO. I still don't know how big the FIFO should be. All right, so how big do I have to make this RX size FIFO to avoid bubbles in the throughput? So you're thinking about this, if I want the absolute minimum size FIFO, because you use a die area here, I want to receive a credit return just as I use up the last credit in here. So I'm like, oh, there's only 1 left. I use it, but good news, that thing came back right at the same time. So, down 1 up 1 in the same cycle, I get to stay at 1. And so I've perfectly matched the smallest possible FIFO size over here. Everything's perfect. Okay, so if it takes n cycles from the data from the TX to RX FIFO, and m cycles for the credit return, then the RX FIFO minimum size is n plus m plus margin. Okay, so what's the margin? Well, this is where it gets a little squishy because these clocks are not perfect. And these FIFOs have the capability of allowing for the clocks to jitter a little bit. And since they're not exactly synchronous, you might get data leaving that FIFO 1 cycle longer than you expect, and it might grab some 2 cycles earlier if the clock advances. So you got to deal with this clock jitter. And you got the same problem with clock domain crosses. You don't need to know exactly as it moves from this core clock domain to the receive clock that it's sent over here. These things are ultimately from the same reference. Otherwise, the scheme's going to fall apart here. But you just don't know, does it take it this one or did it just miss it? So that's the second thing. And then there's the final one, which is never quite sure you didn't count off by one someplace. So generally people stick some extra padding in there just to make sure you don't blow it up here because if there's two big problems. The disastrous problems if you lose data. The bad problems if you cause performance bubbles in your operation. Particularly if this is a real-time system.
Hey, Dave, we're close to 2:30.
Oh, okay. All right, I'll wrap it up. Open source release. Let me tell you, this is great because you don't have to negotiate a license. You talk to Florida, you want a license for using Florida technology. Given legal, this takes absolutely forever. And it's not just Florida, it's Northrop Grumman, it's Boeing, it's everybody else. On open source, it's great. You just download it. Yeah, of course I agree to the Apache 2.0 license. For us, we have to get approval to use open source code. So it's not that simple, but we don't have to get a license, which takes quarters. We have actually used this protocol IP in a test chip that taped out in February. We're going to get this thing back in the summer here, and we'll be able to show that yes, this does work. That's the gold standard that you prove it in silicon. So to wrap it up, it was a great opportunity for innovation in a bunch of different areas. And the chiplet plus an FPGA is a great combination because you only have to design half of the interface. You can do whatever you need to do on the FPGA and hardware in your ASIC, you design half of it, and then you get the FPGA to it down. So that way I don't have to reinvent technology. I can use these sort of technologies that we've developed. And that is it. Are we out of time for questions? No. Okay.
So, I've seen a slide where there is probably the acknowledgement should be at the same cycle for the security verification. Isn't it too hard a constraint when you are considering clock data, the CDC, where two systems are operating at different clocks?
Okay, in the security case here, you don't really have a throughput issue where you want to make sure that full throughput in. It's really, I make a security request, I get a message back, and just put in my thumbs if a message comes back. So in that case, it's using SPILES, the serial protocol, running 50 megahertz. So it's generally not a performance case. When people get up to where they really need real-time control of digital up converters, down converters, they'll use a wider band interface. So in the security case, you just want it in kind of reasonable amount of time you get the response back. So in that event, you basically just wait for the message to get through, and you use your normal block domain crossing techniques to get data across a domain that you're targeting and all of that. Please.
Earlier in the presentation, you were talking about using random numbers in that public-private key encryption. How are you ensuring that those numbers are actually random?
Okay, it's a great question. There are technologies called true random number generators, and these often developed by using random variation in delay to very tightly matched lines. It's one just slightly ahead because of random thermal noise to create a random number. Some of them just use combinatorial loops that are so large that it appears like a random number. We actually did this TRNG that we used to that first approach. We're really trying to get random numbers through very closely matched wires and just see who's ahead, who's not ahead. There's a NIST evaluation suite that you can use on your random. You might be familiar with that. To see, are you random enough? And if you pass this suite here, you can say, yes, I passed in this suite. I can claim that I have a random function. The typical ones like the Unix RAM function, those sort of things are nowhere near at that level of a true randomness. Okay.
The question we have before, there is a gate, like there's a big bubble between when you pass the message and when you get the acknowledgement back. So considering all the errors, margins and paddings, so how big of a clock cycle do you take at it?
How big of a
Like how much time do you wait for between two transactions.
Okay, so in the security case here, it's request response. You wait for the response to come back. So there's really not much issue here. In the AXI case, where you're really like trying to transport data across without any bubbles, generally what people do, depending on how big the FIFO is make sure that you're nowhere close having made a mistake anywhere. And then you run a bunch of simulations on it. And that's, you know, we actually did a lot of measurements on our full round trip delay to come up with the right answer there. And then stick some margin on top of it, which is single digit number of words extra, but enough that you don't have to worry about the overnight.
Any other question? If the timing requirement is not met, between the request and response, what happens to the data, the sensitive data? So does it get to the bus or like you, what exactly do you do?
Well, in that AXI case that I mentioned, okay, the first scenario is you introduce a bubble, it's still protocol correct. You don't lose any data, it's just you apply way too much back pressure. And the guy upstream who was expecting full throughput is something bad's going to happen on that end of it. So that's kind of the bad problem. If you actually overflowed the FIFO, you sent too much and lost data, that's disastrous, catastrophic problem in that case. So you have to prevent against overflow. So that's kind of, the bad and the terrible. And you want to avoid both of them, but the loss of data is absolutely the worst. And that's a non-starter.
Can we add some security policies to govern this situation and make sure that the data is not somehow get exposed to attack? Something like that. Maybe add first-rate data or like make it zero or something from random.
Okay, so there's the NIST standard was just adopted this year on lightweight encryption. And it was meant for very high bandwidth data where you don't have the time to do a heavyweight AES encryption on it. They're thinking of IoT devices. In our case, we're thinking of we've got this high bandwidth bus. We want to protect it against anybody snooping this bus, which is really hard because they're going to look at thousands of bits going over this silicon interposing technology. But suppose you did want to protect it, you could use this kind of technology here. We figure out a way that you have this key generator and basically you introduce it in XOR gate on both sides. You're able to encrypt and then decrypt on the other side. So that's a way we propose that we could do this data protection on the diagram interface. It's usually a pretty big concern because some of the other schemes that were considered such as scrambling either weren't secure or used a lot of power, and you have a lot of bits, maybe a terabyte per second going through here. So you just count up the energy per bit that you're spending on it, you could easily be adding single digit to upper digit watts by encrypting.
Thank you, Leon. Thank you, Dave. Thank we will be here for the other 5-10 minutes if you want to make them. And then we have to go to again, thanks to everyone for joining us.